at the YouTubers, and then I'll be back to you. Thank you. Okay, YouTube is also looks like speaking up our conversation. Good morning, everybody, on the YouTube as well as on the system. And that's of those of you on the Teams, you can't see what I'm gonna share. Please update me if you see what I'm seeing. Not yet, not yet. Just hold on. Okay, this is what I see. Okay, hopefully, let me share with you. On the Teams, can you see what I'm sharing? Basically, this is a Yebo physics tutorial schedule. Lucanio, please update me if you are still in. You do see, your sound is a little bit small. Yeah, good, great. That means this, sorry again, the system is up. That means I can directly go to the next slide. Basically, we wanted today, before I go there, rather, let me let me say something. Today, I will be working on tutorial 4 for PHYV 101 students from question number 5 to 8. This thing is on the work and the energy. The questions are on the YouTube, on the Moodle site. Those of you on the I'm going to change this thing here today. Those of you on YouTube, you must see exactly what we're seeing. Exactly, it is the case. Good, happy. Therefore, I will be working on tutorial number 4. These questions are for the PHYV students. The questions are on the Moodle site. Again, depending on time, I will also discuss about the problems in the physics workbook. This is for FVV student 101. I will go to that one later on though. Therefore, let me go into the questions. This is one of the questions on the, let me maximize. Hopefully they will see exactly what you see. Yes, this is obvious, therefore they see exactly ours. I'm gonna remove my photo a little bit here. This is for the YouTubers, don't worry for the teams. Yeah, the question reads, it says, it's a cart of mass, the mass is given, which is 10 kilogram, is pulled up a rough inclined plane. It is given that the inclined plane is rough. You should be careful in reading that. With an inclination, the angle, with an initial speed of 1.5 meter per second. Okay, it was given a push upward on an inclined plane, which is rough, with a speed of 1.5 meter per second. The pulling force is 100 Newton. It says the force must have to pull it. It is parallel to the inclined plane. You must be careful in reading such a thing. The force is applied parallel to the inclined plane. The inclined plane makes an angle of 30 degrees with respect to the horizontal. And then because it is rough, the system is the inclined plane surface is rough, where this cart is attached to it or sitting on it. It has got a kinetic friction, which is this kinetic friction is about 0.4. I'm gonna hide this thing. She's rotating here. I'm gonna remove 0.4, and then the cart is moved actually the 5 meter up. I think I have, yeah. This is, let's discuss like this. The mass is given. The initial velocity was given. The force with which, this is the force I'm talking, which pulls this thing up, is given. And then the angle of inclination is also given. Mu k is given. The length it moves is given. The first question says, how much work is done by gravitational force? You must carefully see what is the force they are requiring for, the gravitational force. And by now, I hope you remember that the work done by any force is force dot distance d. The force is a applied force, d is a displacement. You see, dot is a dot product, or you could say this one, f d cos theta. That is a general formula that we'll be using throughout. Therefore, you have to figure out what is the force. In this case, it's a gravitational force for part 1. Then we know how far it has moved, which is 5 meters. Then the only thing we wanted is what is the force, and then what is the angle between the direction of the force, in this case gravitational force, and then displacement. The displacement is easy. If this cart comes up here by the action of the force, it must have to be displaced by a distance L. Therefore, the direction of the L is along or parallel to the inclined plane. We know the direction of L. You have to know the direction of the gravitational force. That is the main one. 2, I'm talking about these 2. It also asks us determine the increase in internal energy of the cart inclined system owing to friction. Of course, you could understand. If you pull this object upward, and then it's given that this is rough, you could see that's why I put a dot line. This surface is rough. Therefore, there is a heat involved because this thing is sliding up on it. There is a friction in between. There is a heat. That heat creates a change in internal energy. This is what we are interested in. Then they says, determine the increase in internal energy of this system because of the friction. In the third, it says, how much work is done by the applied force? By the way, that's the easiest. You know the direction of force. You know the direction of displacement. The force is 100 Newton. The displacement is 5 meters. Basically, that one is, this is actually easy. This is 500 joule. We'll calculate one by one anyway. And then in the force, it says, what is the change in kinetic energy of the cart as a whole? Meaning, now it was here with the kinetic energy, with a speed of 1.5 meter per second. It must have reached here with a certain V final. Because of this change in velocity, there is a change in kinetic energy. It's saying, what is the change? No, kinetic energy is scalar. I can't delete here. Kinetic energy is scalar, but we're looking for that one. And then finally, the last question is, what is the speed at that last point? I'm just holding on for you guys to swallow. What is the question all about, first of all? I'm trying to break the question into pieces. The first one, work done due to gravitational force. The second one, the change in internal energy because of friction. The third one, the work done by the applied force, which is easier said. The fourth one, what is the change in kinetic energy as a whole? It doesn't ask us again, what is the final velocity, but it's saying change in kinetic energy. V final square, kinetic energy final minus kinetic energy initial. And then on the last one, what is the final velocity of this object as it climbs up where it is at the last point? Hopefully, did you pick up the question properly? I'm going to go back to my teams. Guys, if you are happy, if you don't happy, please ask a question. If you stop me anytime. Okay, therefore, can I go forward? Yes. Then this is how I go. The first thing is, you could see my stuff. I think my photo is in the wrong place today. I don't know. I'm going to put her there on the YouTubers. You see, I put Newton's second law also. This will help the free body diagram. Drawing the free body diagram helps you. You see what I did? I said, okay, the object is on inclined plane. Always mg sine theta pulls the object down. Because of the direction of the motion is up, the frictional force also push me back. Therefore, that's mu is, what is that? Small f is mu k, which is a frictional force. Mg sine theta down naturally. Mg cos theta is perpendicular to the object with the normal force rather. Normal force and Mg cos theta are on the same line of action. Mg is at certain angle. You know now, if this angle is 20 degree, this angle must be also 20 degree. Find out if you struggle that one. Then the angle, main one is, okay, something displayed down there. Let me go through those ones. Mg cos theta, which is 20 degree, minus n is equals to m1a along y-axis, as opposed to say a along y here. A along y is 0 because it's not going up and down. Using that, you could see that the normal force is mg cos theta, which is 92.1 Newton. Just let's keep that one in case we need it. 2. Force of friction, definition of F for the friction is mu k times n. I've just done my n, good. Therefore, I'm going to know that the frictional force Fk, frictional force Fk is mu k times n. I've got it, that one. I know it's 36.8 Newton. I'll use it soon. Then I must know the angle, which I just started. That angle is 20. This angle is also 20. It is given. Then, this is the first question is, what is the work done due to gravity, mg? You see, mg is down toward the center of the earth. Mg is 20 degrees from the mg cos theta. Of course, you understand that one. If this angle is 920, this angle is 20. However, we are interested in the angle from the all the way to mg. Okay, let me go one step. You'll see what I'm talking. This is a work done due to gravity. The work done due to gravity, therefore I use the definition. F or work done by gravity should be mg, the force, times or dot product. I must be specifying this. This is not times, it's a dot actually. Dot product delta L. The change in length is from there all the way to here, is given in this way. Therefore, the direction is along the inclined plane, but mg is down. The angle between them is from that point all the way to here. I know this one is 20, this one is 90 degree. Therefore, the angle is actually 20 plus 90 degree, which is 110 degrees. This is a tricky part to find the angle between the direction of action of the mg, which is gravitational, and then the displacement. But if you are good in geometry, you could easily see that that angle is 20, this angle is 90 degree because it's perpendicular. Then the overall angle from that point to this point is basically 20 plus 90, which is 110. The force, we know that what mg is, the mass is given, the gravity is 9.8 I'm using, therefore I got 9.8 times 10 basically, which is times 5 cosine of this one. I get the force, the work done due to gravity is 168 joule, but negative because of the cosine. I'm holding in case somebody has, hey, I don't understand what you're doing. 2, if you don't see any equation in between. Second was to find what is the increase in internal energy because of that friction. You see, I've done my job though. I know the frictional force, it's down. I know the displacement, it's up. The angle between them is actually 180 degree. Therefore, cosine of 180 degrees is -1. I could put this one negative in principle because always the frictional force is negative. I better say negative this much. But just yet use 36.8 from this calculation. Displacement is 5. Just I forgot to put that negative in principle because the angle is f. That small f is to the left. The other one is to the right. The angle is 180 degree. Cosine of 180 degrees -1. Therefore, the change in the internal energy is 184 joule. I put it negative because it's not cooling down. Please remember that negative actually is just a sign. Change in internal energy is positive. It's a heat is formed. That heat formation is basically to tell you that there is energy lost because of that friction, and therefore negative. Again, I'm continuing. Let me just pop into the YouTubers in case they have question. And most of the time I forget the YouTubers in principle. YouTuber, oh, there are people are watching. Thank you for liking. Please guys, interfere me. I'll come back in between to chat to see if anybody is chatting. Just interfere me, please. I'll be watching your chat. Okay, at this stage, thank you for the likes though. I'll continue. I don't see any chat. Let me just say hey. Hi, just to show you where the chat window will appear. Guys, you get it there. Good. Let's continue then. We have done one, you have done two. The third is actually talking about work done by the applied force. I said to you, that is the easiest of all. Force up, displacement in the same direction. The angle between them is 0. Cosine of 0 is 1. F dot delta L is 10 times 5, which is 500. Easy. This one is time taking. The fourth is looking for a change in kinetic energy. But I wish I kept this one a little bit to display the equation. But if you're good in the theory part, which I believe Professor Tim has gone thoroughly, change in kinetic energy of such a system is basically the addition of all work done by the system. How many works are there? The frictional force has got a work done. The force has got a work done. The gravity also has got a force done. And the normal force also has got a work done. Therefore, the change in kinetic energy is actually the sum of the actions of all the forces. Frictional force, gravity, normal force, and then applied force. But remember, some of them are negative. As you could see here, the frictional force is naturally negative. You see, even though I forgot to put sign there, I have it here. See, therefore, if I pull it in, I basically say, okay, the friction is negative, the 500 is positive, the work done due to the gravity is negative naturally, which the calculation give me. Then you see F normal is 0. You might ask, oh, why is the normal component didn't do any work? That could be your answer. That would be your answer. Those of you in the teams, at least you could comment to it. Why is the work done due to the normal force is 0? Whereas I've got, for F dot delta L, I've got negative 184. For F dot, that F is a small f frictional force. This is applied force dot delta L. I've got 500. For the weight, I've got 680, 168. What am I talking? This one. But I put Wn is 0. Why could I do that? Do you have any idea? YouTubers, or those of you who will be listening to this conversation after it will be uploaded. By the way, we are uploading it directly on the YouTube, straightforward. Therefore, you will be listening to our conversation there. Think to yourself. Stop the video and then think of it. Why is Wn is 0? Now I'm going to give you the answer. The answer is that the normal force is up. The displacement is perpendicular to the normal force. Therefore, work done is 0 because the cosine of the angle between the normal force and the direction of displacement is 90 degrees. Cosine of 90 degrees is 0. Therefore, that work done due to the normal force is 0. The only work done we have is therefore 1, 2, 3. If you add, you only get 148 joule. This is the change in kinetic energy. I'm holding again. If somebody has some question, I wish if you guys are online right now, you could have said, oh, okay, why you say so? If you are not online, obviously, and then you're listening to this video once again, if you have any question, you could send me email. I don't have problem. I'll explain it to you. Good. Let's go forward. The last one is what is the speed of the car at the destination, at the last point. It was there, it has got initial kinetic energy of 1.5 meter per second square. Now it's going to have an final velocity, obvious. Therefore, the change in kinetic energy is half of mv, what is that, half mv square at final minus half mv square at initial. We know the overall delta kinetic energy is 148. Therefore, you equate this one to it, and then don't I have another one? Yeah. Therefore, solve for V final. V final should be, you could easily see that half mv square is equals to half mv final square, what I mean, equals to 148 plus half mv initial square. That is where this plus comes in. 0.5 is coming from half, 10 is the mass, the initial speed is 1.5, it's given, and then I'm taking that m to that side, therefore it's 2, that 2 is from under, it comes that side, 2 times the difference of that 2 divided by m. If you put together, you know the mass, you simply get that the final speed of this car at the destination is equals to 5.6 meter per second. Happy? Thank you again. I'm checking on the YouTubers. Thank you for the like. People saying, oh, I like it. Okay, I like it either. Also, question number 5 on PHYV 101. We are done. Those of you in Teams, Lucanio, are you still with me? Yes, you, Lucanio, you are still with me. Are you okay? You all right? Lucanio? Mr. Lucanio. Okay, I'm teasing in between. Maybe he's going to bring a glass of water. I'm teasing. I wanted to drink water. That's what I want to say. Just to a little bit lubricate my... I've got a long way to speak. Up to 2, I'll be with you. Okay, therefore I need to have a sip of water in between. Okay, guys, if I don't get any interruption, if nobody says, hey, I don't know what you're doing, I'm going to continue. Next, question number 6 on the PHYV 101. See, I always say in the class, or while it's online like this, that half of the answers, by the way, is in the question. Understanding the question and then setting up the strategy is half of the answer. You almost got the answer if you finish those ones. This one says, the coefficient of friction between the block of mass M1, that is M1, and the surface is this much. Meaning, this guy is actually, it's not smooth. This one has got a roughness. Yeah? It's rough. And then it says the system start at rest. Oh, good, thank you. V initial is equal to 0. And then what is the speed of the ball of mass M2, which is M2 by the way, you could see there, M2, when it has fallen a distance of 1.5 meter, meaning it's going to come here when it fall a distance of about 1.5 meter. Of course, you could see the velocity is going to be down. It will have a certain velocity V. That's what you are looking for. And then doesn't say anything. You have to keep now in mind that when this thing happen, because this thing is connected by a tension, that rope, this must be coming around here by then. In doing so, there must be a heat generated between here. There is a frictional force. And then even though the system doesn't give me any information, I'm going to consider this pulley is massless and frictionless. It doesn't do anything. The pulley is just going to be hanging there. It doesn't affect. Meaning this tension that puts this thing to the right is the same as to this tension as long as the pulley is frictionless and massless. It's not turning, massless, that's where it is coming. The pulley is not turning, and then there is no friction. But actually we're exaggerating this thing. There is no way that pulley is massless and frictionless. But for the first year, we always take them slowly. We say, don't worry about the pulley. Therefore, when this object falls down, this one moves to the right, the tension here is the same as to that tension, then you could see the velocity with which this object 2 move is the same as to the velocity with that object 1 move, because they are interlocked. This is the assumption that will be going. Therefore, how are you going to find the speed with which these objects move? And then remember, we are in the work energy. Therefore, you have to think, okay, can I use a conservation of energy? Yes. The conservation of energy state is that the energy of the system at the beginning is the same as to the energy of at the last. What are the energies we know of? There is a potential energy, there is a kinetic energy, there is a frictional force which causes energy also. These three, we have to be careful. That's where we're going. If I push you forward, I said, okay, let me first take this assumption that the M2 is moving down, M1 is moving to the right, then the pulley has got massless and has no mass and the friction. This thing is going to happen like this. This is what I'm putting. So, okay, how many things I have? I have a frictional force. You can go with me with the cursor now. I've got a frictional force that pulls this object backward. However, the work then due to friction on this mass M1 is proportional to the frictional force times the displacement. You might say, oh, where do you get that h? I know. If this object falls by a distance of h, M2 I mean, the same way that mass M1 has to move a distance of h because the tensions are all the same. You agree? Hopefully yes. Therefore, this displacement down h is the same as the displacement of M1. Good. I know the distance. What are the forces? The forces are actually mu times mg. That is a normal force on M1. You could see if I have to do it here, normal force is up, down is mg. Because this object M1 is not moving up and down, then I say the frictional force F is equals to mu times the normal force. Then mu into that normal force is mg. Therefore, this expression is small f times the displacement h. Therefore, I've got the work done due to friction on M1 at final. Plus, because M1 is in a state of motion, it must have M1 V1 final square. Therefore, I've got two energies associated with M1. It is height is not changing. You must be careful here. Okay, let's go. How for M1? It has got work done due to friction, which is equals to mu k mg times displacement h. It has got work done due to kinetic energy, which is equals to half m1 v1 square. Work done due to gravity gh is 0 because this thing is sliding horizontally from this point to that point. Therefore, work done due to gravity or potential energy, let me call it this one. I can't delete by the way here, I don't know how. Work done due to potential energy is 0. Change in, rather I better say, change in work done due to potential energy is 0 for M1. What about for M2? Again, the same for M2. Does it have a frictional force? No, this thing is not touching. Therefore, it must have a kinetic energy, have M2 V2 square, and then this is to do with kinetic energy, and then it has also have mgh due to the potential energy. That's what you see here. But because it's going down, my potential energy is negative. Lucanio and the friend, you guys, okay, I must keep it there. No. Rather, yeah. Where am I? Yeah, I'm here. Yeah. Lucanio and the friend on the Teams, YouTubers, a little bit, there is a network problem. YouTube receives small data says. YouTubers are in trouble, but it's going to resolve soon, by the way, because of internet. But those people on Teams, you must follow what I'm talking. Therefore, that negative, You see, this is not M1. Oh, error. This is M2. M2GH for M2. Not potential energy 1. This also potential energy 2. You see, I haven't edited my equations properly. That is 2. That is 2. Then a very good information. Because the M1 and the M2 are linked by the tension, they are hooked together one another. The friction is no friction on the pulley. V1 is equal to V2. They have the same speed. Be careful, otherwise you run into problem. With this assumption, I know now everything is all right. Set it up. I said, okay, good then. From work energy theorem, change in potential energy plus change in kinetic energy must be equals to work done due to friction, or change in potential energy plus change in kinetic energy plus work done due to friction must give me 0. Energy is conserved, neither created nor destroyed. What do I have then? For the kinetic energy final, remember the initially it was 0, nothing is happening. I'm talking about like this. One more, please. Saying slow down. Okay, I'm talking here. Initially, nothing is happening. There narrows nothing. Initially, everything is 0. There is no initial stuff. Therefore, I'm coming here. Initially, there is nothing. Finally, there is a kinetic energy due to mass 1. There is a kinetic energy due to mass 2. There is a potential energy due to mass 2, but it's negative because it's coming down. Then there is due to friction. I put my equation careful here. If you make a sign mistake, you end up with negative. Careful there. Half m v1 square plus half m v2 square minus m2gh, because it is dropping. That's where the negative comes. Equals to the work done due to friction, which is negative. It is dissipated heat. Dissipated heat that goes off from the overall system. Therefore, by the way, somebody must pull this thing. Of course, you could understand. To set it in motion. You pulled it. Your pulling will make this one to accelerate down. Plus, it creates a friction between M1 and the floor. This is basically changing kinetic energy of the system, which is mv1 plus 2, minus the drop in potential energy must be equal to negative of the work done due to friction. That's all the formula. Then we have agreed that because this thing is connected by the tension, and the tension is the same, they have the same speed, I could remove 2 and the V1 and the V2 from it. Now I have got the common velocity as common. Then I solve for V. That V would be the square root of this one. You could easily see. Take this one, add to the right, or basically m2gh minus mu k m1g times h. If you reorder, you easily see this equation is correct. I'm happy about it. And then basically what I'm left with is just plug values. The values therefore is as a given. I put together, this is what I get. I got a speed of 3.74 meter per second square. Does it make sense for you? It should. That's what I asked myself. First of all, I said, okay, it was given, it is this one, and then I got the speed of this much. How do I check? Just check the forces and everything that you're putting. This one actually you can't see. It only says that it dropped by 1.5 meter. Energy is conserved. If you put back that velocity, everything must give you 0 here. If you add up all the kinetic energies plus change all in the potential energies, all the work done due to friction, it must give you 0. Hopefully if you use V and I do this thing, it will be correct. I'm happy. You should be. An equation for this one, I'm just holding on in case somebody is listening to this conversation. If you are listening to this video or watching this video after it has been uploaded, stop it and then rehearse about it. Why did I do? How do you fix these equations? Just ask yourself a question and then does it make sense though? You know what? I believe you guys, especially PHYV students, they wrote test yesterday. They ran away from the physics today. Basically, they're saying, I'm tired of that physics, let me not go. That's why I don't see so many students today online, I believe. Last week there was a lot. And the next week they're going to ask me again. And they, please, can you go back to tutorial number 4? Because I don't understand it, because they are not here. And I will not going to go back anyway. They will listen to this conversation, which is uploaded onto the YouTube. Good. Number 7. What is this one? I didn't read about this one. I did this workout, by the way. I wrote it last week, therefore I forgot about it actually. It says an 820 Newton Marine in basic training club climbs a 12-meter vertical rope at a constant speed of this much. Constant speed, zero acceleration. What is the power output? I think this is the easiest question. Power is equal to work done divided by time, isn't it? Power, P, power is work done, W, divided by time, T. Energy, rate, the rate at which energy is dissipated or work done by time. Work done, if this guy is climbing at a constant speed, it's not accelerating. Therefore, it's a simply force times distance. The force is given, which is equal to force times the distance divided by time. What is the force? Therefore, this one is 820 820 times, he climbed 12 meters. I'm going to forget about the unit, divided by 8, therefore. Didn't I have answer? Yeah, basically, she's there. Yeah, easy. I don't know why they put this one here. It's because it's quite simple. I'm not gonna undermine your understanding. That is easy. Question number 8. Hey, I'm going fast today. In half an hour, not half an hour, 39 minutes, I go through all the PHYV students' question. Easy weasy. Happy for me. I will finish early because nobody is interfering me. Okay. Question number 8. It says this is the last question for the PHYV student, guys, and let me read. A 10 kilogram block on a horizontal, frictionless. This time there is no friction. This thing is a smooth. Okay, frictionless is attached to a light spring. There is a spring K with a spring constant K. It's given a 0.8 Newton kilonewton per meter. This one is the same as to 800 Newton per meter. Remember, this is kilo. Don't forget about it. It's a 10 raised to 3. 1000 times 0.8 is 800. I know that one. Good. The block is initially at rest. Okay, thank you. V initial is V naught is equal to 0. And then it is at equilibrium. That means it's not stretching. X is equal to 0 also. X is equal to 0. Remember, the Hooke's law, force is equal to the Hooke's law equation, or F is equal to minus Kx. That X is 0 at the beginning. Therefore, there is nothing. It's at equilibrium. Good. With the magnitude of P, 80 Newton. Now you have got P is equal to 80 Newton. You're going to pull it up. When you pull it, of course, you could see that this string is going to stretch. And then because of that stretch, it has got a X, some displacement. That's where it is going, I believe. Parallel to the surface, okay? What is the speed of the block when it is 13 centimeters from its equilibrium position? It says when X now is 0.13 meter, I convert quickly into SI unit the moment I see non-SI units, that one. And then kind of non-SI, which is kilonewton. I go into Newton directly fast. It will help me to pick up everything together. Now the question is, when this thing is stretched by a distance of 0.13 meter, what is the velocity? There is a multiple choice down here. I don't look into it at this stage. I'm going to basically say, I know what you're talking. What should I use? And then I should remember that, it's a work energy conservation. The work done at the beginning, which is energy at the beginning, must be equal to energy at final. Energy at beginning is nothing at this stage. The kinetic energy is 0, potential energy is 0. It's not pulled yet. But the moment you pull with this force, the spring will push you back. And then there is no friction in between the surface and this thing. It is good. No frictional force. The only force involved is therefore the applied force plus the spring constant. Agree? Then with this assumption, I'm going to go forward. Then I said, okay, then the work then due to the applied force Fp is force times the delta L. And then again, I must know that the spring also moves apart, meaning it's now stretched. The for work energy theorem, which I put it here, this equation which I'm reading, is given by changing potential energy plus changing kinetic energy as long as there is no friction. Work then due to P, which is a force done by the applied force, must be P, the force times the distance it moves. Okay, the distance it moves is 30 centimeters. Of course, you could see must be equal to half mv squared plus half kx squared. I know L, which is x in this case. X and L are equal. Therefore, what do I don't have? V I don't have. Solve for V. Easy. Then basically you could see that half mv squared is equal to PL minus half kx squared. Then V must be equal to V squared rather, must be 2 over m into PL minus half kx squared. Then instead of a square, you put under the square root. This is the equation. Happy. PL 0.5 is the 4 half, da da da. Put my values in, you guys engineers, therefore I'm not going to go where is each value going. The P is 80, X is 0.13, the half is 0.5, the kilonewton is that is K, which is 800 is that of K, 0.12 square is Kx squared divided by the mass. I got a speed of 0.85 meter per second. Therefore, if I go back, the answer must be that one. The answer must be A. Hey, in exactly 43 minutes, I finished how many questions? Question number 5, number 6, number 7, and number 8. 4 questions. It's enough. Every one question is about 10 minutes, basically. 10 plus. Okay, let me say 11. 11 times, yeah. PHYV. Lucanio, those of you on Teams, guys, have you benefited from our conversation? Are you guys there? Maybe I'm sure my microphone, speaker, you guys, you could hear me, isn't it? I was worried that if I was not audible to you guys on the Teams. I believe it is audible because my system indicates me that my microphone is okay, my speaker is okay. You guys, you're just keeping quiet, I believe. Lucanio, is that the case? You guys, you hear me? Okay, maybe I'm just teaching myself today. Okay, PHYV, I have done. I'm done. Finished. I'm going to go into FVV student. I'm going to discard actually. I'm not going to save this one. And if I go back for PHYV, no, FVV, do I have it here? Physics. Yeah, I have it. Good, great. This is for the FVV student. By the way, those of you PHYV also, this thing is good actually. Dr. Lindsay has got nice questions inside. I'll show you what I mean nice. I'll be working on 8.4. This is 6. 8.4. 8.345, I believe. Yeah, we've done through this one. 8.1, 8.2, 8.3 is finished. Then, I said, yeah. I'm going to start with 8.4. You see here. I'll be starting here, 8.4. Therefore, we're basically going a little bit behind from the PHYV student, but this has got nice information. If you read through, I'm not going to go one by one. She has all the information, nicely organized. If gravitational force, for example, which is G-wise of M1 over M2, it is always attractive force. G is given, you know what it is. For example, by the way, the acceleration due to gravity G is calculated using this concept. Mg is equal to G-wise of M1, M2 over R squared. M is M of the mass of the Earth. That M is an object above the surface of the Earth, just on the surface. MA is equals to mg. If you put this equation, G is actually G times mass of the Earth divided by radius of the Earth. G is universal gravitational constant. You see how beautiful it is. This is acceleration due to gravity on the surface of the Earth because of the radius. You know what it says? That means if you have, and this is our Earth which we live on, if you are on a certain distance h, and then you rotating about the Earth, actually your acceleration due to gravity is no more 9.8. It's actually mg, instead of this one, instead of r square, you're supposed to say h plus r the whole square. That equation will change. But on the surface of the Earth, h is 0. Therefore, this acceleration due to gravity on the surface of the Earth is 8.98. I'm tired, I believe. 9.81 meter per second square on the surface of the Earth. But if you go away, at a certain point, the acceleration due to gravity is 0. It makes sense. If you go to space, there is no gravity. You see, therefore, simple mathematics give you something impressive. Okay, your weight becomes m times g on the surface of the Earth. If you go to space, you become weightless. How interesting is it? You see, just by knowing simple mathematics, you could predict what sort of mass do you have if you are going to space. You become massless because gravity is 0. The weight becomes you becomes massless basically. Yeah, I like these conceptual questions. She put for you the weight of an object is a force, not a mass. The weight, you see, she told about the weight. Fg is not a weight, rather not a mass, rather is a force. You go through these ones. I'm not gonna spend time with it. It's just reading. If an object is on inclined plane, she has shown you nicely where is the normal force is perpendicular to mg, but the mg is what did she call it? F due to C contact. I hope she's saying FC. I don't know what it means. Guys, read. Mg sine theta is down. Mg cos theta is like this, in this way rather. You will see that's what N is normal force. I'm not going to bother also that one. I'm just going to go frictional force always in the backward. Fk is equal to force due to friction. I'm going to zoom in. You could see it's mu k times normal force. Normal force is mg, but it's not always mg. If it is flat on the surface, it's mg. If it is inclined, mg cos theta. I hope you guys go through this one. She have everything there. Then also she said, okay, careful of Newton's law. F is equals to ma. If it is not accelerating, the net force must be equal to 0. If it is accelerating, the net force must be equal to ma. Therefore, you have always F along x causes acceleration along x. F along y also causes acceleration in the y. Remember, force is a vector, acceleration also a vector. Choose your system properly. That's what she's implying here. I'm not going to sit with you with this assumption. Rather, I am here. I want to solve through these problems. Okay? Basically applying 8.4 to 8.6, that is where I was going. Let's slowly go through these problems then. Those of my student on PHYV, you guys still on? Okay, good. It will help you guys. It's good questions actually. Therefore, if I zoom a little bit more so that those on the YouTube can see it. Let me see what it look like. Good. Yeah, they could see it. Yeah. I'm gonna zoom a bit on question number 1. Okay. Let's zoom here. This is what YouTubers see. Therefore, I'm interested there. Is this one is easy, I believe. You know what I said? I didn't read though. But just on, because she has indicated everything, that's what I'm saying easy. If a rocket says, slide down in a, slide shown in a fig, that means you go, this is a rocket, is going fast. It starts with only one rocket burning, okay, one of the rockets is burning, that's where the thrust coming, it move with the magnitude of its acceleration. What is the magnitude of its acceleration? It's saying, assume that the mass of the system is 2,100 kilogram. The thrust the force with which the thrust force, of course, is given. 2.4 times 10 raised to 4 Newton, powerful thrust force. And then the force of friction is opposing the motion, which is 650 Newton. You know what I would have done? If it is me, I'm going to zoom a bit up, so that you guys, I want to have a space. Yeah, I'm going to write it here. I will say, okay, if this thing is moving, there is a force, let me pull it even. Can't I? Yeah, take a red pen. Come on. Blue, red. Why she is not writing? Let me check here. Please write on it. Guys, I'm gonna discard it and then open again. I don't know why she misbehaved. Worksheet book. And then can I write yes now? At the list. Okay. Yeah, that's where I wanted. Yeah, and then that's where I am. Yeah, here. What we wanted is, there is an applied force. F applied is because of the thrust, it is T. Force of F due to friction, which is always negative, remember, it is 650 Newton. Therefore, if I make this one just like an object, a ball, this is a force applied force, and then the friction is always backward. This is small force. And then the whole system accelerated forward. Then I say, okay, good then. If it is accelerating forward, which is she implied to me, then the sum of all forces along X must be equal to MA. Then I know the forces are always along X. In this case, acceleration should be along X. Then I say this one implies that the applied force F, which is T, good, which is tension T, minus the frictional force F. This is the net force. That equation must be equal to M times A. Then I say my acceleration must be equal to T minus F over M, which equals to T is 2. Let me zoom a bit in. Yeah, 2.4 times 10 raised to 4 minus 650 divided by 2100. That should be your answer. If you don't trust, I'm gonna open. I don't have calculator with me, therefore I always do with Excel. Those of you on the Teams, you could see what I'm doing. Therefore I say, okay, what is the force? 2.4 times 10 raised to 4 equals to, I'm killing time actually. Then the other one is, what is that? The force is 650, and then the mass is what is that? 2100. Then I said to you the acceleration must be equals to the R1 minus this one. I'm gonna put in bracket. This is what you do with your calculator either, divided by the mass. This must be 11.11 or 11.12 meter per second square. You see, correct. It's easy actually, 11.12 meter per second square. Good, then we are happy. Are you happy? I am. If you are not, let me know. Okay, and then question number 2. That is question. Is this the same? Question number 3, what I'm looking at. Is this the same? What says? The rocket sled shown. Okay, it's again the same. Accelerate at the rate of this one. Oh, now the acceleration is given. It is passenger. That's young girl, I believe, because she has, or a man, I don't know, has a mass of 75 kilogram. Girls are not that heavy. This is a young boy. Let's say 75 kilogram boy is sitting inside, but it's accelerating at 49. Wow, this is a big for acceleration. You see, phew. Then of course your seat in that case, if you feel what is going on, your seat is going to push you forward with this sort of acceleration. It says calculate the horizontal component of the force the seat exerted against the body. Of course, you could see what, as I said, it's like this now. If you think of it, this is a chair, and then you're sitting here, this is your head, your body. The chair actually push you forward with a certain force. That's what your body feels. Remember, your gravity also is mg. We're going to work out. I don't think they are looking for mg at this stage. Therefore, we're interested in that force. Then, what is the equation actually? I didn't know. I didn't read. You see, I'm bad. This is a thing. Acceleration is given. A is given, which is 49 meter per second square. Guys, you know the unit. Has got the mass. Mass is 75 kg. Therefore, what's the force then? Force horizontal. Of course, that force F is equals to mass times acceleration. It's easy. Force is along x. Therefore, mass is given. Go back to my Excel. What is it? 49 times 75. That's all what I want. Is equals to 49. 49. The acceleration times the mass, which is 75. 3675. This one is 3675 Newton. That is what this person feels on his body. It's a very huge force actually. And what she said, 3.68 times 10 raised to 3. Let's go. Just to compare, the dot is there, 1, 2, 3. Therefore, this is the same as to 3.6. Let's round off. Instead of 5, this one go 8 times 10 raised to 3 Newton. Therefore, correct? It's actually easy. Then, something comes in. Calculate the direction and the magnitude of the force that the seat exerts against the body. Now it's a bit more complicated. This is the horizontal force. I'm not supposed to remove. Remember, there is a mass times gravity also down. We need mg. The seat, now if you are seated, the force of your bum is also experiencing a force because of the gravity. Therefore, the force is actually down and that way. This one is F, applied force. This one is mg. Then the angle between them is not going to be down though. I'm lying. It's a certain angle though. Because you are not sitting. This object is accelerating. It's actually at a certain angle. I could see it's not going to be straight down. From my understanding, I could easily see that the force is not going to be straight down. It's going to be in a certain way with certain angle theta, because remember you are kind of leaning backward because the force is pulling you. Then acceleration due to gravity is certain angle. Okay. Therefore, what do you get? The force is 3750. Let's go get that force first. I didn't go through this one. mg. Let's see what is the m is. I wish I used it here. M is 75. Gravity, G small g. G is equals to 9.8. Therefore, the force of gravity, F, this is force due to applied force. Let me call it capital F. This mg is, I don't know what to call it. Let me call it this one. This times that. 750. What is this one? The magnitude. How can I get the magnitude? If the forces are certain, I believe that is the Fy. What do I get? Let me just, I don't know. I didn't do it. What is this? Hold on. I'm taking the net force would be SQRT square root of Fy square. Let me just do it. I don't know what she's doing. Fy square plus Fx square. That is this one square. Under square root, what do I get? 3.748. Okay, let me first compare. What was her value? Just to see. 3750. We get 3747. And you know why? I believe she's not using 9.8. What if I use 10? You see. She's using a gravity 10 or something. Is it 3750? Or the angle? Guys, come on. Where am I? I'm gonna, yes, yeah. Yeah. We got the net force actually. 3. Go back to my Excel. Forgot. In my head, I'm thinking all those threes. Let's not do what she did. I'm gonna use this one. 3740. 3749.8 Newton. That's what I get. If I use gravity 9.8, you see, therefore, then it is the net force is going to be horizontal, below the horizontal that way because of that one, and then this one. Please go through this one nicely. I'm done for the kind of tired also. Check number 4. If I'm not interfered, I'm going to gallop through. I'm actually, you see, I've got a horse. My horse doesn't have that controller. It's simply moving. My controller is you. What is this question? Question number 4 is talking about a bathroom scale. It says bathroom scale, you know, that normal scale that you keep in bathroom. Every day you go there and they stand on it and you measure your weight. If you have, I used it to do when I was young. I stopped it. I know now overweight. Therefore, I gave up in controlling my weight. I'm teasing, but you do by now. Therefore, we're talking about the bathroom scale. Simple one. You put it there, you jump on it, and then you know your weight. It provides a quantitative reading of how much it must push upward to support your weight. You see, she's saying that think of it has got a spring in, kind of, with a certain spring constant, and then you go stand on it. When you stand on it, this is one of your leg, the other leg is here, then it's actually going to compress. When you compress it down, it must push you up to keep you leveled. Then it's saying it provides a quantitative reading of how much it push you upward to support your weight. You see, that forces we're talking. What would you see on the dial, on the reading? And now you're looking, some of them are digital, some of them are analog. It looks like this is analog, it turns. And then you say, oh, okay, you are around, I'm telling you my weight, about 80 kilogram. Or yours may be 56. I'm guessing you guys, you are young. Or close to 60. You read this one. Now she asks you a question. Oh, what do you think? If you take this bathroom scale and then put it in a way, for each of the following scenario, indicate if you will see a value greater than, equal to, or less than your weight at rest. Oh, when is that scenario? Oh, okay. I think I kind of have idea where she is going. It should be to do with the and it should be to do with this, you know, kind of last year also. You going into elevator, by the way. Yeah, good. I guessed. You're thinking of putting, just do this thing. By the way, it's a very, very interesting. Take your little bathroom scale, bring it with you. It's small. You could carry. We have here in the lab also. Put in the elevator, stand on it. What happened to the reading if the elevator is going up or the elevator is going down? Do you think it's going to read different? That's what she's asking you. The elevator accelerates upward. In this case, you are here. How did I draw that one? I'm saying this is a surface of your elevator. No, your spring. This is your way where you're standing. One of your leg, the other leg, and then you are actually standing in an elevator. That means this thing is placed on the base of the elevator. Instead of you standing here on the floor, you're actually standing on your weight. And then you still could read your reading. First put it in on the elevator. Elevator is not moving. Stand on. Take your reading. Let's say, oh, okay, weight 1 or mass 1. Let's call it, because it's tell you in the kilogram, mass 1. It's divided by gravity anyway. You have it. Now it says the elevator, I don't want to close. The elevator is going upward. Means now the elevator has got an acceleration. If elevator is going up, what happened to your reading? Is it going to increase or is it going to decrease? I almost tempted to leave it with you guys for you to do this experiment. It's fun. You could go in and then try to check. But I could give you the mathematics behind so that you don't need to do the experiment. You see, remember what we said. The reading of the scale, because of your weight, it has to counterbalance your weight, has to apply some force. That force is up. If I now show you in terms of mathematics, not doing the experiment, there is a force 1 due to your counterbalance. Let's call it f of x due to you compressing it down. Additionally, that there is actually mass times acceleration, where this acceleration is acceleration of the lift. Therefore, if actually accelerate is up, you increase a force into the scale, therefore you read more than what you read now. Therefore, if you call it this one is M2, M2 is greater than M1. That's what I say. Do you think, no, M2 is actually less than M1? I want you to do the experiment. What if the accelerator now, or the elevator moves down? Instead of up there, the force up is due to f of x. Remember that x is a spring that you have to compress down. Then this guy is actually moving down, the acceleration down here. F net, therefore, here, F net is actually here, by the way. F net is on the top one, is fx plus ma, the acceleration of the going up. Therefore, it is the net force is higher. Here, the net force is F due to the spring minus F due to the acceleration. You see? Therefore, you actually weighs less. You become less. Of course, you could feel, instead of doing and taking your scale with you in the elevator, just sense what you feel when you are in the elevator. When the elevator starts to move upward, actually, you become heavier, as if something is pushing you up. You become heavier for yourself. If the elevator is going down, you could see that, you become weightless and you actually kind of on the air. You could feel this one. Therefore, it says what you just can read if the elevator accelerates at g. You see, it says it is accelerated at g. This one is actually giving a very good information. If it is moving with the gravity down and you are mg, the weight of you is mg minus ma, which is equal to f net. You see, if A is equal to G, F net equal to 0, the scale becomes non-reading at all. Therefore, 4.2, the reading will decrease because the acceleration is down, the applied force is up. Applied force is due to the spring, which is push you up. However, if G is equal to acceleration, the acceleration with which the elevator is moving down is equal to the acceleration due to gravity on your weight, it becomes balanced, you become weightless. Happy? If not, ask me a question. I'll explain to you more. 4.3, it says elevator moves upward at constant speed. You see, if it is constant speed, guys, you know now, in a rectilinear motion, constant speed means if v is 0, therefore acceleration, which is defined as dv by dt, is equal to 0. No acceleration, no force. Meaning F applied, F all or overall force is equal to F of x. F of x is due to the spring. Your weight is constant. The reading is therefore the same reading before and after, because acceleration is constant. This reading, m1 is equal to m2. Here, m2 is less than m1. m2 is your weight or your mass that dial is indicating to you when the elevator is accelerating upward or downward. At this point, at 4.3, when it is constant, your weight is this, or your mass is the same mass to the same mass that you would, that scale gave you before the motion starts. Happy? Here it says the elevator moves the downward at a constant speed. Again, this also, if it is constant speed, no acceleration, m1 is equal to m2. Remember, m1 is equal to m2 is the mass of you when you measure yourself on the scale, plus when you measure yourself in the elevator, where the elevator is accelerating, decelerating, moving with a constant speed, and then a constant speed up and down anyway. Okay, here the elevator decelerates while it's moving downward. Haha. It's a deceleration, accelerate. You here, m2 is greater than m1 because at least it's moving, but it's not moving down, but it is going slower and slower. You become heavier and heavier because here the acceleration is down but negative. Deceleration is the same as to that guy here. Think of it. Your elevator has got a problem. While it is moving down, if you go like stopping, you knock yourself onto the base, meaning you increase your weight. If you are standing on the scale, by then the scale will shoot up because you pushed it more high, more down. You understand what I mean? If not, please guys, go through. The elevator decelerates while moving up. Now look, it's accelerating up and then it hiccup again. You become weightless. Here, therefore, m2 is less than m1. I am happy if you guys go through this question thoroughly and then understand very well. It's a very good question actually. And she gave you also about PHET simulation, ramp, force and the motion. The link is available on Moodle. I'm not gonna do for you. Please, you guys go through this one. I'm not gonna bother. Then, yeah, you will do this one. Basically, that is the end of what I am planning for, isn't it? Yeah, it continues. Let me go back. Yeah, this is all with that simulation. I'm not gonna do with that one. You have to go over there. And what is this one? 8 point, I think. Repeat, it says. What is this? I didn't read this one at all. Repeat the previous problem with the constant falling forth of data. Ft cos theta is equal to ma. I don't know what it is. Is this? I think, did I jump any equation here? It's 8.5. Oh, okay, 8.5. Oh, yeah. I'm gonna go 5.1, 5.2, and then 6. Oh, question 6 is different though. A constant in a winter sport event is pushing, a constant in a winter spring is pushing 45 kilogram block ice across a frozen lake as shown in the figure 521a. Where is this one? Calculate the minimum force F he must exert to get the block moving. I think, yeah, I must do this one. I thought I'm done. I'm done. Let me first go check that. Yeah, this is the one. What is it? There is an angle. Therefore, the force on this one by there to the right is, and then to the left, because he is not putting horizontal. This one is F cos theta. Down is, you see, I'm decomposing this vector. Down is Fy. Horizontal is Fx. Therefore, Fx is F cos theta. Horizontal down is F sin theta. Then, what is the question? The question is, I'm going back to that page. Here. I know. Okay, therefore, a mass is given here. M is 45 kilogram of ice across a frozen lake as shown. Okay, I've seen it. This is in A. We know the force. Calculate the minimum force F that must exert to get a block moving. Okay, the answer is 51 Newton. She said, how do we get it? B, what is the magnitude of the acceleration once it starts to move if the force is maintained? Okay, let's work out this one. In principle, it doesn't have friction. In one transport event pushes this much of force across a frozen lake. Okay, the question is calculate the minimum force F. Okay, the minimum force required. Therefore, F, remember the diagram. Let me redraw it here. If I bring it into this page, that is a ice. Mg is gonna be down, and then this one must be F cos theta. Then there is a component of the force which is F sine theta. Therefore, this we interested in what is the minimum force required for this thing just to start to move. Just start to move in that direction. Obvious, this is the direction of motion. Therefore, I will say F cos theta must be equals to MA. It's just started. Therefore, what do I have? What if I say, that what keeps this thing is assuming there is no friction. It must be equals to mg. What do I get if I say so? Let me bring it in. What is the mass is 45. What is this one? Is equals to, let me first write. M is, I could read it from me, 45. G, acceleration due to gravity G I'm taking, is 9.8. I don't know if she takes 10 or 9.8. The angle is theta. Let me call it ANG angle, which is 20 degree. What was it? I must go into it to this one, but here that not 25 degree. Therefore, back to it. No, under. I'm here. Okay, 25. The angle is 25. Then cosine of 25 is equals to cosine, this is XL of that angle times, don't worry what I'm doing here, if your calculator will give you, this is pi divided by 180 degree. Remember, I'm changing from radian to angle. The cosine of 25 is this much. F cos theta must be equals to mg. Then I'm thinking of the F must be equals to mg over cos theta. I believe. Let me check if I get it right. This times this divided by cosine of that angle. What do I get? 486. Oh no. 51 Newton. What did I go wrong? Huh? I think I know. What about my F sine theta doing? Yeah. What about that one? Oh. What is F sine theta, by the way? Let me go. What is sine of this angle? Equals to, this is cos. And then I'm going to have sine. Guys, help me if you are online. What is sine of this angle? Sine 25 times pi divided by 180. Let's get that one. Therefore, what I'm interested is F cos theta plus equals to mg plus F sin theta, then F into cos theta minus sin theta must be equals to mg, then F must be equals to mg over cos theta minus sin theta. You can't see what I'm doing, but I will come to you once I get this thing alright, which is equals to, now I'll do it equals to, what is it, that times this divided by, I'm gonna get big number though, I know something is wrong here. Boom boom, what did I say? Cos minus sine, this minus that, and 11. Guys, help me, I don't know what I'm doing. What do you say? How do you get 51? Those of you YouTubers and then teams, I need help. I need help. Somebody help me. I'm teasing actually. Oh. Okay. I need help. Lucanio, are you gonna jump? It says, in a winter sport, an event pushes 45 kilogram block of ice across a frozen lake as shown in the figure. That figure I've drawn you for you here. F equals theta is to the right, F sine theta is to the down. It's pushing down. Mg is also down. And then this object moved that way. She said calculate the minimum force, the smallest force required for this object to move. But I'm not given frictional force. Any idea? Lucania? Or YouTubers? Let me go to my YouTube. Help! I need help today. I'm trying to motivate you guys also to just to show you that yes, I should be thinking before I go in. What do you say? Oh, okay. I'm also wanted to okay. Let me just visit. I've been sitting for the last 1.5 hours now. Just want to go out and then a little bit refresh and then come back in. I'm gonna leave everything running. Please work through this problem and what is the minimum force required for this object to start moving. I'll see you in 5 minutes maybe. I'm gonna come back. am back. But my system is blank. Yeah, good. My YouTubers and 2 people left. Okay, I'm back. You guys on the Teams, you are still there. This is a question on hand. I don't know either how to solve this thing. He says a contestant, which is a guy who is contesting in a winter sport event, push 45 kilogram block of ice across a frozen lake as shown in the figure. Calculate the minimum force F he must exert to get the block moving. He says the answer is 51 Newton. I don't know how to get that one. However, I could push you forward. I will say for this thing move in this direction a mass times acceleration. That's what I believe. Mass times acceleration is moving, just start moving. I will say the sum of all forces along x must be equal to mass times acceleration. Remember, we just wanted to start to moving. Therefore, I could rewrite this one. Then this basically actually I will say it has to balance the frictional force. Okay, this everything must balance the frictional force. Think of what way the frictional force. I don't know the answer, but I'm gonna think of what's coming. This is equal to the frictional force. That's what is holding it up. That frictional force has got. I'm gonna add that normal force N. Then I will say the applied force, in this case F cos theta. I'm gonna write F cos theta minus the frictional force must balance that of the acceleration, or basically the everything. Let me, because it's just starting, I'm going to equate. Rather than doing that, let me say one more equals to force of friction. This is what causes this thing to start. If I do say so, help me please if you have got idea. Then I will say F, okay, let me say F, that small f is mu times the normal force. But my normal force comes from 2. This object is not moving up and down. That normal force must be equals to mg plus f sine theta. You could see where this thing is coming. Or I'll go to the next page and then let's do it there. Sorry. This is what I'm talking. The guy is pushing in this situation. Therefore, is pushing down with f sine theta. F cos theta is that actually what causes this thing accelerate. We are only interested on this one. Then I'm putting here all the forces acting on it. Normal force is up. Frictional force is that way, that small f. I'm saying that F must be equals to normal force mu of friction, let me call kinetic, times normal force, mu k times to set it into motion. What's the normal force? Because this thing is not going up and down along y-axis, N must be equals to mg plus f sine theta, because half of the force is did I lost? That's the bad side of working with this tablet. Once it go off, it will discard everything. Don't worry, I'll be back soon. 8.4, that's where I was. I think that's, is it not here? Yeah, one more. Yeah, it's here. Yeah, this is the question I was working on. Then the graph is down, and then we're here. I will do it properly even. The force is down. The force is down. F sine theta gonna be this way. F sine theta. F cos theta is that way. F cos theta. Mg is down. And then normal force is up. I was saying, because this object doesn't move up and down, the sum of all forces along y is equal to 0. This implies that the normal force must be equals to mg plus f sine theta. Then the frictional force, if this thing is moving that way, the frictional force go that way. F must be equals to mu k times n, where that n is a normal force, is equals to mu k sine theta. No, slow down. Mg plus f sine theta. Okay, this is what I have. Then I said, okay, let's go back to the question. The question is here, question number 6, which I say I don't know how to. She said this contestant who is doing it in a winter sport event is pushing a 45 kilogram. Mass is given. The M. Can't I write? Again, she's stuck. Come on, my tablet. If I go out, she's not gonna write. Oh. Why she stopped writing? Oh. Again, I'm gonna go out. Page 25, that's where I am. I'm gonna go out and I come back again. Discard. Go back to my tablet. I don't know why she broke. And then I'm gonna go to page 25. Somebody who gonna help me? I could see a noise. Funzo, somebody's just joining us. We are here, by the way. I'm gonna rewrite F cos theta, F sin theta, mg, and then the object move that way, the frictional force is this way. That's where we are. Go back to my page. Then I said, calculate the minimum force F he must exert. Oh, somebody is just joining us. Let me even a little bit make this thing more. Guys, guests, I've got 2 guests. Help me on the teams. Check the following. The following from FEVV student, this is where the question comes. Look, let's read the question together. I'm kind of stuck. This is a contestant, somebody who is contesting in a winter sport event, pushes a mass of this mass. Let me draw now here. The image is on the bottom one, 45 kg. At certain angle, I could see now the force is coming this way. The angle is 20 degree. Therefore, I said the force which is parallel is gonna push this way. This is F cos theta. Then which is down is F sin theta. And then this thing is moving. The question is, it asks, what is the minimum force? The minimum force if this contestant has to apply on this object just for the block to start to move. The answer is 51 Newton. I find it difficult to get where that comes in. But the following is what I think, how it is done. I know this thing, the F cos theta is causing, the sum of all forces along X must be equals to MA. For this thing to just start moving, it must be equal to the frictional force. You have to balance the frictional force, basically. Please correct me or come with the idea if you have better way. Therefore, the F along X is actually the applied force F cos theta must be equals to the frictional force. That frictional force, mu times normal force. Mu is mu of K, the kinetic friction. But I have to say that the normal force, because this thing is not moving up and down, that is a normal force. Down there is mg. That normal force must be mg plus F sin theta. Then, if I put into my equation, F cos theta must be equals to mu mg plus mu F sin theta. Then I bring that one there with the F to the right. F is common into cos theta minus mu sin theta must be equals to mu mg. Then I say my F must be equals to mu mg over cos theta minus mu sin theta. But my worry is I don't have mu. Can I say the mu is small? Then it end up. I don't know how to work. What do you say? This is from FVV, by the way. If you guys on the teams, you are from PHYV, we have gone through the PHYV equation actually. You guys, you came late. Therefore, this is how far I'm going to push you here. What else did I forgot to use? Contestant in a winter sport event pushes this kilogram block across da da da. How do I get 51 Newton? I'll even go too simple that F sine theta, F cos theta is equal to mg, it doesn't work. If I forgot about the friction, equals to mg divided by cos theta, m is 45 divided by times 9.8 is a big number. I did it with the Excel here just to show you. M is that one, G is this one. If I simplify my equation, say hey, it's gonna be this times this divided by the cosine of the angle, this one. I got a value of 486 rather, which is not true. This is how far I go, but I need a mu to go through. You see, if you get the force, the B part is easy. If you know the force, mass times acceleration, you easily get it. But how is the 51 Newton force is going to come? What else? Is this thing linked to the question I jumped? No. Does the weight of an object ever change in direction? This is a simulation. I jumped that one. Question number 5 I didn't do even. This is all what I say here. I believe we need mu to go through. Unless I don't know something saying that mu is, what is the mu of a winter sport? Is it generally known? But I could go forward a little bit. For these two force to be minimum, you see what I mean? I could go just in mathematics. For this force to be minimum, this must be maximum. Therefore, I could also say that the cos theta minus mu sine theta must be maximum. For when this thing is maximum, cos theta must be much greater than mu sine theta. I could go like that. Then if that is the case, mu must be or tan theta must be greater than mu. Then if I go this way, tan of this, you see what I'm writing, tan of this one is sine divided by, let me say, tan must be equals to a sine over cosine, this divided by that, I got 0.46, that is tan. Then if I say, okay, let me assume that mu is equals to 0.44, mu is equal to 0.44, then what do I get? Let's assume that this, I'm just simplifying mu. I'm jumping up and down actually. Based on this calculation, is proportional to tan theta. This must be equals to that. Then if I multiply mg by this, what you will get? This must be equals to that one times this one, half of it. I get 256. I don't get even the 51. Therefore, I don't know how she gets 51, honestly. But I believe the process is this one. To minimize the force, I must maximize the bottom one. Okay, if I maximize the bottom one, maybe I'm exaggerating things. I say that tan theta must be much greater than mu. Therefore, mu must be much less than that one. If I take that one, what is the smallest number I could go? mg times what equals to 51, and I'm gonna go that one. This is the overall. This divided by 51, the answer she put, I'm trying to find. How can I get a mu of 9 point something, which is not mu divided by this one must give you a little bit of a number. That's all I say. I don't know, honestly. That's how far I take you. I don't know how she got 51, but this is a way to do. Guys, if you don't assist me, I'm passing it. Okay, let's go forward. What else she have? Or I'm gonna ask too many questions again. Yeah, you know what I'm gonna do? I'm gonna ask Mr. What is that? Tomorrow is Arnold. I'm gonna ask Arnold to continue from where I stopped. Tired and then beaten. I'm gonna finish with this one. Have a good day. This is a teamy, guys. I'm gonna stop the teams first. Okay, teams is done.